On behalf of Karnataka Physics Association, we welcome all of you to this talk. And it is our fortune that Dr. Ramya has agreed to give a talk on understanding the formation and evolution of galaxies in the era of large telescopes. And of course, she is our Bangalore University student only. And sometime back, Srinath Ratnakumar was expressing that she is very good even in Kannada also. I think some members, in case if they ask the clarifications or questions in Kannada, no doubt she would be able to answer in Kannada also. Anyway, I think like normally Professor Kagali was welcoming all these days, and today he has given me an opportunity to talk to you to start with the program. Of course, we are doing this online talk almost from 2.5 years, October 23. And of course, almost every Sunday, this program is going on. And today, we have a very good speaker, Dr. Ramya Sethuram. Like what I heard that she is very good in English as well as in Kannada. Of course, before we go, you have, madam, you have 50 minutes talk, and after that you will have 10 minutes for clarifications or comments or questions or anything. And before we go for that, I request Dr. Sudhindra HS to introduce the speaker. Sir, it is to you, sir.
Thank you, sir. It's an honor and a great privilege for me to introduce Dr. Ramya Sethuram, today's speaker at Karnataka Physics Association, co-hosted by Gnanadhara. First of all, I would like to congratulate on Women's Day, madam. It's a coincidence that we have a woman speaker today. I would like to read out a brief biodata. Ramya Sethuram obtained PhD in Astrophysics from IIA and Bangalore University in the area of dwarf galaxies in 2012. She did 2 postdocs in Institute of Astrophysics, IAP, in Paris in 2012 to 2013 in the field of quasars and at Shanghai Astronomical Observatory. So it's also called as SHAO, China, working on low surface brightness galaxies from 2014 to 2018. She then moved back to IIA as a project scientist of the 30-meter telescope project and is based at India TMT Coordination Center in the IIA campus, Bangalore, since then. She is continuing her scientific research in galaxies. She is also the work package manager for building the Wide Field Optical Spectrograph WFOS to be installed on TMT and a lead architect of the instrument control software for WFOS. She also serves as one of the main members of the IAA outreach team responsible for public outreach for the TMT project. So this is about Madam's biodata. I thank once again for KPA and President, Vice President, and also P. Nagaraj for giving me an opportunity to introduce the speaker. Thank you, sir.
Madam, now you can start your.
Yeah, thank you, sir. I will share my screen.
Srinath is present. Srinath K.R.
Sir, morning, sir. Present, sir.
Okay, sir. Please welcome.
Okay. I'll start now. Um, uh, Thank
Yes,
you.
yes. Please
Thank
go
you,
ahead.
KPA members, for giving me this opportunity to present some understanding of galaxy formation and evolution, and the effort which the astronomers are taking to build large telescope, why they are building large telescope, and what is India's contribution, whether India is doing anything towards this endeavor. So I'll be presenting that today here. So since the audience is varied physicist, physicists, so I thought I'll go from the basics. So you can stop me anytime if you think it is too basic. I can speed up. Thank you for this opportunity, and I wish everybody happy Women's Day, all the women present here. This is the overview of my talk. I'll give an introduction to the observable universe, how fascinating it is. I'll give a glimpse of it. I have tried to keep most of the images or pictures as true as possible, except for they are color coded. Apart from that, it is mostly taken from all the telescopes around the world. Our current understanding of galaxy formation theories, how telescopes are spread across the world, which help us to understand these theories, to understand the formation theories, and what is the way forward with building large telescopes and its instruments. And one last slide for engaging students in the making of this telescope.
सर बहुत सारी खबरें हैं ईरान से लेकर के अमेरिका और भारत तक की बात होगी। बात भारत में जिस तरीके की सियासत है उसमें भी कई अहम चीजें हैं। एक तरफ कांग्रेस पार्टी
Background.
जरूरी मुद्दे बार बार सवाल के रूप में देश के सामने रख
So
रही
I
है।
just want to
सरकार सब सवाल पूछती है लेकिन सरकार की वही चुप्पी
I
जो
just want to start.
11 साल पहले देखी थी, 12 साल पहले देखी
That's
थी,
the good,
वो आज
Dr.
तक
Raman
नहीं
sir.
आ रही है। जब हम क्यों नहीं
Please
दे पा रहे हैं ये सब
start
देखिए
the
Someone, disturbance is
सियासी
moving.
घटनाक्रम है उन पर भी बात होगी। शुरुआत हम जरा ईरान से करते हैं। सर ईरान की
I'll continue.
ये जो
So,
युद्ध ईरान का चल
what
रहा है
you
इस
see
समय
here
अमेरिका और
is
इजराइल के
an
साथ,
infographic image of how the
कैसे
universe is
देखें
formed
क्योंकि
and
अब
how
कोई
it has
9 दिन हो गए
expanded.
हैं उस युद्ध को
Um,
और 9वें
So,
दिन में जब वो
what
युद्ध है
was there was a Big Bang explosion at the beginning of the universe, which led to some amount of quantum fluctuations. Then there was nothing. The dark ages was spread over there during some time. Then the starting of quarks, the quarks were formed. Quarks merged to form the elementary particles, which we know as the protons, neutrons, and electrons. And from there on, they fused together to they fused together to form other, slowly the first stars, the first galaxies. So we expect the first stars and first galaxies to have formed 400 million years after the Big Bang. And after that, the galaxies or the first stars which formed, they continue to evolve by hierarchical merging. So the two galaxies merged to form bigger galaxies in mass and in size. So like that, the galaxy started evolving, and what we see here right now is all expanded universe. Along with that, we have well-formed galaxies. So this is the kind of picture we understand that the universe has gone through. So, what is the effect of Big Bang? The effect of Big Bang is that the universe is expanding. Galaxies are moving further away from each other, and the further apart they are, the greater their recession velocities are. So, what we call them as the Hubble velocities or Hubble constant or Hubble velocities, V is equal to h naught into d, where V is the recession velocity and d is the distance to galaxy. So, if the velocity what we expect or what we measure, like similar to the Doppler shift, if it is greater, which means to say that the object is receding. This is called as the cosmological Big Bang effect. It is because of the universe itself being expanded. So, how do we measure the effect of this expanding universe? We see that if a galaxy is having a very high velocity, systemic velocity, we see that it is at a higher redshift. So high velocity implies higher redshift, and higher redshift is nothing but a higher, larger distance. So V is equal to h naught d is what is the basic equation we use, where h naught is the Hubble constant. I'll come back to the h naught value in later slides when we further understand about dark matter and dark energy. So here in this equation on the bottom right, what I have shown is when the c is constant, what we have is because the c is constant, the larger distances introduces longer light travel time. So, what we mean to say is that when we have high Z galaxies, which which means to say that they have taken a long time to travel to us, which means to say they left the light where they left their parent object when they were very young, and by the time they reach to us, the universe has also expanded quite a lot, and the universe has aged. So when we say high Z or high redshift galaxies, we mean to say that the galaxies, the light we are receiving now is when the galaxy was young. So this is what we say as looking back in time. And when we look back in time, we see very young systems in the universe. So that is the effect of Big Bang, that the universe is expanding. So keeping this in mind, we want to show you the JWST simulations, the James Webb Space Telescope simulations of lambda CDM cosmology and what it means of the reionization era. As you saw, there was only absolutely nothing at the beginning, and then slowly the quarks and dark matter connecting between two galaxies or groups of galaxies, and they are also merging to form larger systems. So this is what the idea is of galaxy formation. So coming to the individual systems, galaxies, how do we define them? They are agglomeration of stars, gas, dust, dark matter, dark energy, etc. So what you see here on the right is a true image of several of these galaxies. We have billions of galaxies, as you saw in the simulations itself, and each galaxy may have billions of stars. So, so if we look at these galaxies, you see that they could be having gas, and the small dots could be star forming regions where new stars are being born, and the uh, dark lines, or what we call as lanes, they are called as dust lanes. And closer to dust lanes, you have a lot of gas and stars being a lot of gas, which will combine or gravitationally fall under its own gravity to form new stars. And they are all held together by gravity. On the bottom left, what I show is our understanding of the universe formation and evolution. And the circle I have marked there in red shows what we are seeing right now at z is equal to zero, whatever at redshift zero. Higher the z value implies we are looking very back in time or almost the beginning of the universe. So that idea you should keep in mind. So, as I told, it is this. So, where do the stars form? Because the stars, this is one of the view from James Webb Space Telescope, which is a Carina Nebula. Here you can see a lot of dust and newly forming stars. This nebula is about 7.5 kilo light years away, and one light year we define as 9.5 to 10 to the 12 kilometers or 10 trillion kilometers approximately. So these are the locations where new stars are formed because of gas, dust, and dark gas and dust collapsing. Um, when I say gas, it is hydrogen, and hydrogen and helium. Beyond hydrogen and helium, we call everything as metals. So these are the locations or sites where the new stars are being formed in the galaxy. This is one close-up view. Then, as I told you, inside this gas and dust, the stars are getting formed. So this is a view of a nebula, a Eagle Nebula, you could think of, and that in different wavelength bands. How the same object looks in different wavelength bands. What you see on the left is the Hubble image, Hubble Space Telescope, which is a 2-meter telescope, and on the in the middle you see Hubble's near IR image, which is less than 2 micron. Beyond 2 micron, and in a line emission, you see the third image of the Eagle Nebula. Again, the orientation is slightly tilted. And on the right, top right, you see the same nebula in mid-IR. So mid-IR, when I say there is polycyclic aromatic hydrocarbons at 3.6 micron, 8 micron, 12 micron. So those the same nebula looks totally different uh, in different wavelength bands. So in fact, when we observe an object, we want to take the multi-wavelength approach, where from UV to near IR, even radio, microwave, and submillimeter, we would like to observe, get a complete census, to get a complete census of what is happening in these systems. So this is another view of how a galaxy would look at different wavelengths. In radio, we see the synchrotron emission. In infrared, we see like old stars emitting, and in visible, we have the pure light. And in ultraviolet, it is also newly formed stars of about 100 million years or a few hundred million years age. And in X-ray, we see the high energy being emitted from the center, which is probably because of the black holes. So coming to the classification, it was Hubble who first tried to classify these several galaxies. He was the first to also say that hint that these galaxies are not within the Milky Way; they are outside the nebula. They are external nebula, is what he understood. And he observed a lot of galaxies and tried to morphologically classify them in what we call it as a Hubble tuning fork diagram. So in the Hubble tuning fork diagram, you see on the left you have elliptical galaxies, and on the right it branches out into two. One is a spiral system, and the other is a spiral barred system. So in these systems, you in the spiral systems you see again a differentiation like SA, SB, SC, depending on the number of spiral arms, how tightly it is wound, whether it has a central bulge or not. Depending on that, we further divide it into SA, SB, SC. SC, you can see the spiral arm is totally open and not very prominent also. In SBA, you see that there is a bar. Similarly, in SBB and SBC, you see there is a B. B stands for, capital B stands for bar. So this is the way he tried to classify. He thought that the evolution of galaxies goes from left to right, but later on, due to lambda CDM cosmology, I'll come to it. One of the inferences we understand is that, and also from a lot of n-body simulations of spiral systems merging together, we understand that spirals merge to form ellipticals. Though the diagram was drawn in this way, the evolution seems to happen from spirals to ellipticals. When two spirals merge, that is a very violent reaction where the spiral arms are destroyed. Lot of gas is used up in quick star formation episodes, and what we end up is ellipticals, which are gas poor systems. There is no gas to form new stars, and it is also systems with having old stars in it. So when I say all that, I would also say what is the Milky Way structure. Milky Way is a barred spiral, And this is an artist impression how the Milky Way looks and what are the different arms it may be having, what are the different kinds of arms. But when we see the real image of Milky Way, we can take only the picture of one of the spiral arms or a few spiral arms. And this is the Gaia view, European Space Observatory view of Milky Way and its streams. When I say streams, as I mentioned to you, hierarchical galaxy formation, this is the best evidence what we have that the larger galaxies will eat away smaller dwarf kind of systems. Two galaxies merge together. That is what is seen here. So when the galaxies merge, they have a violent reaction where the galaxy system is stripped completely. And the arcs you see here in each of these is the stripped smaller galaxies coming closer or getting merged into our Milky Way system. And the central band is one of the spirals of Milky Way. So this is LMC and SMC. These are Large Magellanic and Small Magellanic Cloud. They are neighbors to Milky Way. As you can see, the central thing is the Milky Way, and LMC is Large Magellanic Cloud, and SMC is a Small Magellanic Cloud. They too are interacting through a bridge, what is called as a bridge. And because the galaxy, these two are dwarf galaxies, and our Milky Way is a much larger system that is being pulled, and what you see as the leftover material from the LMC SMT together is what is a Magellanic stream. So this is all these galaxies merge with our Milky Way. So our neighbor is Andromeda M31. This is also an equally strong and massive spiral galaxy with, and probably at some time later, Milky Way and Andromeda will merge. So whatever images I am showing are true images from Hubble Space Telescope. This is another image where it shows that many galaxies, not only one or two galaxies, many galaxies also merged, as I showed you in the simulations. So the simulations match to our understanding, at least until today, in many cases. So when I say the galaxies have a lot of stars, and stars are the ones which do a lot of nucleosynthesis. That is, a nuclear fusion is always happening inside the stars, which synthesizes other elements. On the right, you can see the periodic table, and the periodic table is color coded, and the colors represent what is the celestial system which has created these elements. As you can see, when we had the Big Bang, after the Big Bang only created hydrogen, helium, and a bit of lithium, primordial. Then it is the stars, the dying stars, massive stars, which have created the massive nucleus, basically. All the massive nucleus in purple are because of merging neutron stars, and low mass stars only produce these elements. So basically, we are all products of stardust. So when these stars evolve and burst out into novae, supernovae, that material pollutes the atmosphere, and new stars form from that atmosphere of the polluted system. And from there, we have higher elements, and these higher elements are creating what is further into planets and other solar systems. So we are basically stardust, and these processes, some are called the slow process, some are called the intermediate process, and some are called the rapid process. And these processes show how higher elements, higher chemical elements are formed when the stars burst. On the top left, what I have shown you is the evolution of stars. So when we say a particular age of a galaxy, when we mention the age of the galaxy, what we mean is that we see what is the oldest kind of star present in that galaxy, and that age of the star we assign to the galaxy. So that is how we say the star formation history and age and metallicity also. So what you see here as a main band is the main sequence where the hydrogen is burning into helium. Once all the hydrogen in the core of the star is burnt into helium, what you have is a subgiant and a giant branch, where the helium in the core starts to burn. If the mass of the initial star is high, or the luminosity is high, then the star goes into what is known as a supergiant phase and a supernova phase. If the star is something similar to our star, then our sun, it ends up as a white dwarf. So the onion structure of chemical synthesis goes as hydrogen, helium, carbon, neon, oxygen, silicon, iron. So from top to bottom. So the core, once it is hydrogen form, once it is iron form, it is the binding energy of iron, as we know, is very high, and further nucleosynthesis is not possible, and the star fades as white dwarfs with a low luminosity, comes down and sits at the white dwarf. So that is what we are trying to understand. We are trying to understand what is the kind of elements present, what could be the age of the system, what we are observing, whether it could be stars or whether it could be galaxies, and what is the luminosity, or what is the um, what is the brightness which the star has. So those are the three important things. So once we understand about the stars in the galaxy, the stars inside each stars, if we understand, we can apply that knowledge to our understanding of galaxy formation and evolution. So galaxy formation here, as the infographic or a picture shows here, is nothing but it is an interplay between inflow of gas or accretion of gas, new gas into the system, the consumption of the gas into stars. Once the gas enters or is consumed by the stars, then it is locked for almost 10 gigayear, as we have seen, because it undergoes nuclear fusion and stellar evolution. So that is the consumption of gas, what we talk about. And finally, it is also the outflow of gas. When the during the stellar evolution, we see that the massive stars end up as an explosion, as an exploding system, as a supernova, as a nova. So that time, a lot of material is thrown out back into the lot of material is thrown out back into the into the surrounding. So that's how the galaxy forms and evolves. So this is an interplay between all the three kinds of processes which will determine what the galaxy is. And for us to understand what the galaxy is, we try to understand galaxies through something called as the scaling relations. How much is the star formed, or how much is the star getting formed right now? What is its stellar mass, total mass in stars? What is the metallicity of these? What is the metallicity of these stars? What is the metallicity of the gas? Will give us an idea of what the process is happening and in what evolution stage the galaxy is. On the top left, what you see is a two branch of what is called as how much is the star being formed, and what is the star which is already formed, the galaxies which are already formed. There is no much gas in it left, so that forms another branch. So the top branch, what we call here, sorry, my cursor is not moving for some reason. So what you, on the top left, what you see as plotted in the line is a blue sequence where still the star formation is happening within the galaxy. They are forming stars actively. While the lower branch in the same plot, what you see is dead galaxies, or red and dead galaxies is what is called. They don't have much gas. That is why the star formation values are very low, and but they are massive systems, as you can see from the x-axis. They are in the log stellar mass values. They are very massive systems. Log stellar mass in terms of M-sun values. So, so the bottom is low star formation but high stellar mass. And on the top, you have also star forming galaxies. So we think that the stars, once all the gas is consumed into the stars, then there is not enough gas, and the galaxy evolves to become a red or dead galaxies. On the right, we understand that the metallicity is also what we see if the metallicity is high in the galaxies. Metallicity, when I mean metals, the amount or the abundance of metals greater than hydrogen and helium, we see that the galaxies are massive and gas depleted if they have also high metals. So the gas rich systems are still evolving, so they form the lower part of the curve. So that is how we try to understand galaxy formation and evolution. So to understand these things, okay, let me complete the total picture by telling a few things about dark matter and dark energy. It was actually Zwicky in 1933 itself when he tried to understand about the coma clusters. He found that the velocities of a few galaxies are high as large as 1000 kilometers per second, which means coma cluster means large number of group of galaxies held together by gravity. So some of the galaxies had very high velocities, recession velocities, you can systemic velocities, you can call them. So when if it is 1000 kilometers per second, those are much higher than the escape velocity of the whole cluster. So they should have been flown away or blown away or flown away from the cluster, but still they are held together, which means to say that there is an additional mass already there. He called it Denkel materie, or the dark matter, what we understand now. So this is an invisible matter. We cannot see it through any form of electromagnetic radiation. It interacts only through gravity. So we don't understand it. But in 1970, Vera Rubin and Ken Ford now gave the exact evidence or via galaxy rotation curves, which is shown in the top plot here. For a galaxy, we can measure uh, assuming centripetal force is balanced by the gravitational force. We can measure its rotational velocity, which is root of gm by r. And after the mass is not or sufficient mass is after you go from the center of the galaxy to the outskirts, then you expect that the curve to fall down. Keplerian, which is V is proportional to r power minus half, which is the expected curve. But as you see that the galaxies continue the velocity, the rotational velocity continues to be flat even at a very large radii from the center of the galaxy, where you don't see visible matter at all. So even you consider all kinds of matter, whether it is stars matter or whether it is simple hydrogen gas, still the curve doesn't seem to fall down as per the Keplerian law. So this is what confirmed, gave a good confirmation for people that there is an additional matter, which is a dark matter. So these, in the bottom plot, in the bottom figure, what I show you is a realistic um, dark matter map plotted on top of galaxies. This is about 800,000 galaxies from JWST sextans data, and they have measured the dark matter. Wherever there is a massive cluster, the dark matter, which is seen in blue color, is also larger. So bottom also there is a plot where Hubble also had mapped this, and now James Webb Telescope is also mapping more clearly that wherever you see white dots, you see that the dark matter is also more there. So that is what is the influence. Now there is not only, so we now have stars, we have gas, we have understood there is also dust because of the dust lens. We have understood there is something called as dark matter, which is holding these galaxies together. And apart from that, there is something called as dark energy also. We don't understand dark energy at all. Sir, is there a question? I'll continue.
Yeah, yeah, please
You can stop
continue,
here.
ma'am. Toward the end, we can take it up.
Yeah. So there is something called as the dark energy, which we absolutely don't understand. So, but the composition of dark energy is also what we don't understand. We call it as a vacuum energy density. We think that 70% of the universe is filled with this energy density. Dark matter takes up 26%, and stars, gas, and dust all put together, or baryonic matter, what we can call it, takes only 4%. So we require this dark matter, dark energy, because we get the inference from our accelerating universe. So when supernovae were measured, the recession velocity and the distances were measured, we see that the slope of this curve is nothing but the Hubble's constant, and we see that for farther and farther systems, we see that the plot shifts up, indicating accelerating universe. So if we have, and that accelerating universe, the energy density is about zero point 0.6, zero point 0.7. When we add up all WL, WB, and WTM, we get a universe which we are seeing right now, which is infinite, spatially flat, and accelerating. So this dark energy is what accelerating the universe. So that is what we understand till now. This is just a high Z universe, JWST's view. We had this similarly with the Hubble also, and James Webb Space Telescope, which is a 6-meter telescope now observing since 2-3 years, is also giving us a very good IR data, mid IR data, and if you see, if you go close and take a look at these systems, they are very tiny. Each dot is a galaxy here. The galaxies which are red and dead also are very farther and formed very early in the universe. So recently, MOM Z14, that is the name of this particular galaxy, it is at a redshift of 14.44. We are all sitting at z is equal to 0, but this is the highest redshift galaxy which is already measured. It is at z is equal to 14.44, which is a very high redshift. The date of this galaxy is formed 280 million years after the Big Bang, which is very early. We expected first stars and galaxies to have formed 400 or 600 million years range, but this is a galaxy which is detected recently. Only January the paper is come out, January 2026, the oldest galaxy in our universe. So you can see the bottom is the spectrum of this particular galaxy, again taken from James Webb, and you see all the lines which are mentioned here. It has all kinds of elements: nitrogen, carbon, helium, oxygen, and carbon. On the right, you see a plot. I don't want to go into the details of this plot, but on the y-axis of this plot, on the top right plot, is nitrogen abundance with respect to oxygen, and on the bottom you can see metallicity. So if the system has higher metals, it will move right in the in this plot. And you can see in the gray where the local galaxies and H2 regions are lying. So that is the curve, that is the dashed curve. But MOM Z14 is showing a very high abundance of nitrogen already. So when compared, it is not falling on the curve where local galaxies are. We think all the metals now, all the galaxies we are seeing are high metals because the stars have synthesized and given out, and we have all the high metals now. But even at a high redshift, highest redshift, 280 million years soon after the Big Bang, we see that MOM Z14 have a very high nitrogen abundance, not hitting even at z is equal to 0, not even. So we need to understand these things. Probably there is some aspect, some pockets where the galaxy formation or the first star formation evolved very differently and in a high speed. So all this information we get from the telescopes. I don't have to tell this audience what the telescopes is, but the size of the telescope, or what we call as the diameter of the primary mirror, is is the most important, or the heart of the telescope. The bigger the size of the primary mirror, better is the sensitivity we get. It goes as d square. That is, the diameter of the primary mirror increases, then we can have better resolution also. It is going as 1.22 lambda by d. Again, d, the larger the d, better is the resolving power of the telescope. So, there are a large number of telescopes around the world already, which is already come, which is, you can see on the left portion of the figure, and on the right portion, what I show is the image of Mauna Kea, where uh, it is fully filled with full number of telescopes. But still, to understand systems of these kinds, we will need a much larger aperture. I will come to that. So, the components of a telescope, we will have a primary mirror, a secondary mirror, an eyepiece or a CCD to collect the image, and a spectrograph. A spectrograph, I don't have to explain to this audience. We will require the spectrograph to understand what kind of chemical composition is there in each of these systems. And as we see the lines here, we try to take the measure the total flux within this line, and that is how we estimate the abundance of each species. So, on the right, what you see is an integral field spectrograph, where we don't put a single slit, but we put multiple slits so that it covers the whole galaxy, and we take multiple spectra. So that is the new trend. That is the integral field spectrograph, which is a very powerful instrument which goes beneath the telescope. So, but it is not as simple. This is one of the image of an optomechanical image, full of electronics, wires, everything put together for a spectrograph, which is a mu spectrograph, which is on VLT. It is the most complicated spectrograph. It seems that it won't work, but fortunately it is working and giving good data, good integral field spectroscopic data. The most complex spectrograph till today. So, coming back to the Hubble 24 diagram, I did not mention about a few other kinds of galaxies which are irregulars, which are innumerable in number. There are, it also contains dwarfs. So, in the hierarchical formation, the dwarfs merge together to form slightly bigger galaxies. Spirals merge together to form ellipticals. So, the evolution goes from right to left. So, to understand when was the first stars really formed, what was its chemical composition, how could such metals already be there in them, we need to observe more of the MOMZ14 kind of systems. For that, the community is building something called as the 30-meter telescope. When I say 30 meter is the diameter of the primary mirror. And this is a rendering of how the telescope would work. It is an Rishi-Fritzsche telescope with 30-meter primary diameter. There is the light from the celestial objects falls parallelly on this primary mirror, gets reflected onto the secondary mirror on top, and which is further focused onto the tertiary mirror. The tertiary mirror is a steering mirror which will push the light into respective Nasmyth platforms, what we call, and on top of Nasmyth platforms sits several science instruments, spectrographs, imagers, and other things. So this is the primary mirror is not a single mirror. 30 meter in diameter cannot be made in a single mirror. It will collapse on its own gravity. So the idea is to make smaller segmented mirrors and attach them together to form one, to act as a monolithic mirror. When I say attach, it is not physically attached. There is always a gap between two segments, that is 2.5 millimeter gap, and it is electromechanically controlled to stay in the same location. So there are 492 segments for this 30-meter telescope. Each segment is a hexagonal shaped, 1.44 meter is the size, and between two segments the gap is 2.5 millimeter. It is precision controlled, and it has adaptive optics capability, and very good instruments associated with it. So there are several institutes and countries involved. India is also a partner in this 30-meter telescope endeavor. So this is one of the rendering of how the fisheye image of how the TMT would look once it is built. It is currently in the construction phase. Caltech, Canada, UC, NAOJ, NAOC are all partners in this. This is a national. This is a national and international collaboration which is going on. So this is how the this is a view of how the instruments will sit. The science instruments will sit on the national platform on either side of the telescope. So when I say adaptive optics, um, I suppose there is already a knowledge of adaptive optics in the audience here. So when the wavefront enters the Earth's atmosphere, the plane wavefront is distorted. The distorted wavefront is what the telescope collects, and we pass it through something called as deformable mirrors. So when the plane wavefront hits the deformable mirrors, or the distorted wavefront hits the deformable mirrors, which is in the opposite shape of that of the wavefront, so we get the plane wavefront, and this plane wavefront is what corrects for the seeing or the blurring effect of the atmosphere. And once the plane wavefront is imaged, we get a very clear picture. On the right is the adaptive optics, how better the galactic center, Sagittarius A star would look. Around Sagittarius A star, it would look with adaptive optics on. So this is the deformable mirrors keep changing. It is a thousand corrections per second. That is the 1,000 hertz per second kind of corrections the deformable mirror goes through. So these are thin mirrors with actuators in the below the mirrors, which will keep on pushing or pulling the support of the mirror. So that's how you have a deformable mirror, and this is via a optomechanical control system also. So India's contribution through several institutes and industry within India, we give about 70% in-kind contribution out of the 10% partnership. And our main contribution is mirror segments. As I told you, these are having about 500 mirror segments. Not each country can make all the 500. So it is equally divided in about 100 mirrors per partner, so that the mirror polishing work is happens in a quick way. So that is about 100 mirror segments are being polished in the facility within IIA near Hoskote, in another campus of IIA. Then we have the segment support assemblies. So what you see in the picture, the top part is the segment, and the bottom part is the segment support assemblies, which holds the segment in the form of which is a 27-point support holding the mirror. This is a mechanical system, but the mirror is glass, so there is no stress. So it is almost a zero stress on top of the mirror. The electronics associated with the control system, the edge sensors, which go into the looping, or when the two mirrors are moving away, it is the edge sensors, which are capacitive sensors, which detect the distortion between the two segments, and that is fed to the actuators, which is on the top, which is on the right, which will correct in turn the shift in the mirror segments. That's how the mirror segments are kept in position. So all these systems which go beneath the primary mirror the heart of the telescope, is all being built in India. Apart from that, as I mentioned to you, wide field optical spectrograph is a science instrument, which is one of the science instruments which is going to take a deeper and faint uh, spectrum of these fainter objects, of objects like MOMS E14. So that is being, we are partners in building that also. Lot of the spectrograph mechanisms are being built in India, and all the software to control whole of the telescope is also built in India. So this is a major contribution. So once the TMT is up, I just want to give you how better the resolution is when compared to HST. This is on the left is the HST image of Andromeda galaxy, but once the TMT with adaptive optics capability comes up, this is how the center of the Andromeda, part of the Andromeda, will look like this with the new number of stars. This is another TMT science case. Actually, I probably the video is not working. We would like to probably image these exoplanets, which are planets present in the outer solar system or a different solar system. The exoplanets, Neptune and super Neptune, super Jupiter kind of spectra have been taken by JWST. What has been not taken or not possible right now is the spectrum of uh, planet habitable world, which is like Earth-like planets, terrestrial planets. That will be possible with TMT. And also, basically, to understand more about the black hole, not only in our own galaxy but in nearby galaxies also, to map the black holes and better understand the mass in it. So these are the three main science goals, but galaxy formation and evolution understanding is also an important goal of TMT. So with that, I would also like to show that India recently has proposed 13.7-meter telescope, which has been approved in the budget this year. So the mirror will be similar to the TMT mirror, the segmented mirror, but the size is 13.7-meter in diameter, and the backend instruments will be similar to the integrated field spectrograph, which is similar to IRIS on TMT, and we will try to build these two in the next decade. So, if anybody is interested for internships, if any of your students are interested for internship, please, they can approach IIA. Yeah, I would like to stop here and take questions if there is.
Yes, if anybody wants to have some clarifications, comments, or questions, please welcome. I think
Madam, I have a question.
Ramya is asking.
Can I ask Nagaraj?
Yes, sir. Go ahead.
Uh, Madam, while determining the age of a galaxy, you were telling that if I heard you properly, you said that you take the age of the oldest star in the galaxy and then determine the age
Correct.
of the galaxy. But
Correct.
then, how do you identify with billions of stars in the
Yeah.
galaxy? So how do you
So,
identify? I mean, how do you single out one star and then determine its age?
yeah, no, sir, you're right. So I didn't go to the details of it. So only the stars within our galaxy and probably the local group galaxies will be able to image star by star. But external galaxies, or what we call as extragalactic systems, what we get is a integrated picture of all the stars. So there we are not able to identify each galaxies. We get an integrated spectrum. That spectrum will have signatures of several elements. For example, we use absorption lines like magnesium 1b. We basically fit the total spectrum, the spectrum between 310 nanometers to 1 micron. We try to do a spectral fitting. Means what? We know how um, stellar population. Okay, I'll tell you from basic. So, if there is a gas which collapses to form stars, it doesn't form individually. It forms in a group. And for clusters, we know that how the stars have evolved using the Hertzsprung diagram and their spectrum. We know how the stars have evolved. So we know for a particular metallicity, for a particular mass, and particular age, how the spectra looks. So we do multiple stellar population analysis or the stellar population synthesis on the integrated spectrum and try to obtain the metallicity and mass, probably star formation rate, all this. So it
But
is.
iron is the last element. I learned of iron is the last element that further. Integration is not possible after that iron. So once, let's say, iron is formed,
No, you.
then it.
Yeah, it, but if it is a the evolution, if it's a massive system, then the core, if the mass is greater than 8 times the solar mass, the core collapses and then rebounds, basically explodes. When it explodes, the material have sufficient time to fuse and form higher elements. Otherwise, there is no way we can form these higher elements. So when the star explodes, in that what I showed as a R process or the rapid process or the slow process, rapid process are the elements which are formed within few seconds, while the slow process are elements which are formed in few thousands of years from the same material. The material which was inside the core completely detonates. So that is one of the phases of a massive star. It's called a core collapse phase. Then we have something called as a supernova type 1a, where it forms because of a binary system. We have a white dwarf and a massive a red giant, probably a red giant kind of a massive star, which is sitting there. White dwarf is also massive. It accretes from this main sequence star or a red giant star. Sufficient material is collected on the surface. When it exceeds the Chandrasekhar's limit, again this will blow out as type 1a supernovae. That is where we also have a lot of iron coming out, basically, type 1a supernova. So all the elements are put either in the star or when the star detonates. So that is.
Sir,
Thank you.
Dodmani,
Thank you.
sir, Vijay Kumar Dodmani.
Yes, sir.
Thank you.
Yes, sir.
Sir,
Go ahead.
Rudraswamy.
Ah,
Hello, sir. Madam,
ಹೇಳಿ sir, ಹೇಳಿ.
Dr. Ramya Sethuram. Nice presentation. I have a very basic question. Does it possible to take actual photograph of our own Milky Way using space telescope since we are part of it? What is your view on this?
No, not all the galaxy image we can take. We can take some of the spiral ones. Through the dust, we cannot peer into. So we are at 8 kiloparsec away from the center of our galaxy. So our sun is located 8 kiloparsec away. So peering into the galaxy is difficult because the dust obscures our view into the center. But it is possible to take images of lot of spiral arms around the galaxy, around our own galaxy, in our own galaxy, and that is how we get the artistic view.
It's artistic view. Okay.
Sir, Dr. Vijay Kumar Dodmani, sir, please go ahead.
Yeah, thank you, sir. Okay, Dr. Ramya, can you hear
Yes, sir.
me?
Yes,
Yeah,
sir.
I hope you remember me. You are alumni of Bangalore University. So we were
course,
there
sir.
in also one of the surf schools also. Anyway, so
Yes,
it
sir.
was a nice talk. Now coming to your this the highest redshift galaxy. So I would like to know if that is an Asian candidate or a normal galaxy.
That's a very good question, sir. It is not an Asian.
It's not an Asian.
Not an Asian. It's just a star-forming galaxy.
And what about the abundances? Is it like subsolar or what kind of elemental abundance?
It is subsolar. I showed a plot. I show that again. One second, sir. Give me a second, sir. Yeah. You can see this plot.
Yeah, I mean, it is not that clear, but it's okay. But what is the spectrum that which wavelength band it is taken? You mentioned the spectrum.
This is a NIRSPEC data. NIRSPEC data JWST because it is high redshift system. All the UV lines have been redshifted to IR.
Yeah.
Near IR, 1 to 2 micron, 1 to 2, 1 to 3 micron. So what you see is all the UV lines which is shifted, and the optical lines will be shifted further out. So out of the band it is, out of the NIRSPEC band. So on the right, what you see is nitrogen abundance, and on the y-axis, and bottom what you see is metallicity. So you can see that solar metallicity is 8.6. But you see, this is something like 7.2. It is subsolar, but even 7.2 is pretty large for such a old galaxy formed very early in time. So that is the doubt.
Yeah, can you answer then the galaxy formation is earlier than the stars or vice versa?
It is a difficult question, sir. So maybe it is very difficult. So
Sir, how about Srinath?
there are two or three scenarios, probably 2 or 3 scenarios working together. So it could be direct collapse of stars to form supernovae, immediate in situ, which has polluted, and then these galaxies might have formed. We don't know, sir. Or directly the gas collapse to form huge galaxies like this. So there are 2 or 3 scenarios. No consensus.
I think can I move on to Srinath, sir? Yes.
Sir, can I ask, sir?
Yes, sir. Yes, sir. Go ahead, sir.
Ramya, it was a very good talk. When it comes to the strengths and capabilities of India in terms of astrophysics, like image building, telescope building, we are very good. But you were mentioning about adaptive optics. I just would like to see, IA is one of the leading institutes in adaptive optics doing some good work. Can you just highlight the strengths, capabilities, and if any weaknesses in adaptive optics engineering, where because in future lot of adaptive optics based telescopes going to come. So you are already last 1 decade, lot of good work is being done in IAA in this field. Just maybe briefly, that's one thing which I wanted to know.
Yes,
It's a
that
new
is
for
good
everybody.
even for the students who are in YouTube. Yes, better.
Yeah. Thank you, Srinath, for this question. Actually, it is a very important question. One of the things, as I mentioned to you here, there is no adaptive optics contribution directly from India. So, which means to say that we are still very nascent in adaptive optics technology. Now, there are some lab experiments which have really worked well, and that has been, we have been trying to put it up on Kavalur telescope, JCBT telescope in Kavalur, which is also IAA's field station. So that activity is going on. Also, the activity towards building an adaptive optics system for a 3.6 meter telescope at Devasthal Aries system is also ongoing. So, building an adaptive system, a system for 30-meter telescope or even 13-meter telescope, which is India's recent endeavor, that will be very challenging unless we completely get hold of the technology either in 2 meter or in 3.6 meter. We cannot go with yeah go on producing for the TMT or a 13-meter telescope. So that is a gray area where India is still in a very nascent stage. Apart from that, the telescope building is, as you told, is good, and instruments for the telescope also the capability is there in India. Adaptive optics is one bottleneck right now.
Thank you, Ramya. Thank you.
Sir, Professor Cogley, sir.
Yeah, thank you very much, Dr. Ramya, for a very nice presentation. I have
Thank
a
you,
few
sir.
general
But
questions.
voice is bit low, sir.
Voice is not clear. I'm using my phone, mobile phone. Is it
It's
okay
okay,
now?
sir.
Better?
Better, better. I can hear, sir. Yeah.
Ah,
And
okay. Can I just want to know if TMT will be able to throw some light on the dark matter formation, just as you are able to get some idea about the early formation of early stars and star galaxy formation. Is it possible to get an idea about the formation of dark matter in the universe with TMT and other instruments? One question.
yeah, there is dark matter map made using JWST data. It is micro lensing, like gravitational lensing
No,
capability
I mean the
using that.
formation stage, early formation, in the early formation, early universe, just
Hmm.
as you are able to catch hold of early stars or early galaxies, is it possible to get an idea of when this dark matter actually began to form? We have no information or no, knowledge about the formation of the early formation of
Formation.
dark matter. Yeah.
Yeah, we have no idea about that,
No
sir.
signatures, no signatures of early formation of dark matter in the universe.
No, sir. This has to go with uh, the identifying of dark matter particles, basically. So, the better the dark matter particles candidates have been identified, the better will be our understanding, and probably, um, yeah. So, one thing is we have to do a more gravitational lensing or micro lensing map, just as JWST has done for even early clusters or formation of clusters. Probably that would help, but I'm really not sure about this.
Yeah, I'm also not sure. Another very important thing is that we always suppose that black hole is there, a massive black hole is there at the center of galaxies. Uh, I mean, any light on how the formation of such black holes at the centers of galaxies is available? How they are
Seed black
formed?
holes, yeah. So that is another area which TMT wants to study, like how the seed black holes or what could be the formation of the seed black holes. Like one of the scenarios is that the first stars immediately collapse to form black holes. That is also there. So there are several scenarios, sir. So we need to understand. With TMT, of course, one of the areas will be that.
Yeah, that's what I asked.
Can I ask a question, please?
Okay, thank you very much. Let somebody else ask some more questions.
Hello, madam.
Go ahead.
Hello, ma'am. How are you?
Yeah, thank you. Happy Women's Day, first of all. A very warm greeting to you on this day, important day. Your talk was very interesting. I have a very basic and a simple question. You are mentioning about various aspects about galaxies, which we have come to know. I mean, many areas which I did not know, have actually realized. And what about this, the large Magellanic clouds? Are they twin galaxies which have merged together and formed a single galaxy? What is this? There was also a supernova explosion in 1987, if I'm right.
Yeah,
In this.
that's right. So LNC, just as I showed you in one of the pictures, LNC also has streams falling into it. So you can see this picture.
Yeah, I'm not able to see. Screen.
The screen is not shared.
Yeah, it's not shared.
Sorry, yeah. So you can see this picture now. This is a Milky Way, and all the arcs are stripped of dwarf galaxies, The dwarf galaxies which are stripped of its
Madam,
material
it is
and
not,
falling into.
screen is not shared.
Not shared still. Still it is sharing, it is taking time.
Okay.
Screen share, yeah, it has started, but
Now is it okay?
it's okay.
No.
No, not yet.
Okay, in one of the images which I showed you, the Milky Way with its several of dwarf galaxies in the form of arcs which are falling into the Milky Way, and the material which is being stripped off. Right. Similarly, LMC also has several of the arcs falling into LMC, and SMC itself is merging with the LMC. Small Magellanic Cloud is self merging with LMC.
So is it supposed to be the nearest galaxy to our Milky Way
Yeah,
galaxy?
SMC
That
and
is,
LMC are our companions, yes.
yeah,
Dwarf companions, yeah.
thank you. Thank you.
Srinivas Babu, sir? Yeah, please ask.
Sir.
Yeah, yeah.
Uh, Thank you very much, madam. It's a very good presentation. One observation here is you have shown the pictures of near IR and micro, which is appearing highly resolvable and multicolor. How near IR and IR, which appears a gray color image, are you doing any pseudo coloring or any mixing of colors for the images?
So how these are made is the images are taken in multiple filters. So we match the resolution of the images to one resolution or the bad resolution, and then we stack them on top of other. We merge the images of different filters. So we color code them, sometimes pseudo color, sometimes real color. RGB is given for RGB colors. Otherwise, near IR also takes different colors. So basically, we observe in different filters. The exposure times, the sizes of the stars are all matched, and then they are stacked together. They are merged together. They are put one on top of another.
So image fusion you are doing with the multiple.
Yeah, you can say that.
Okay, madam.
Multiple filters.
Thank you, madam. Thank you.
Yes, anybody is there to ask if there are no questions? I
I have a
think,
question. Excuse me. Am I
yeah,
audible?
yeah, Dr. Mallesh.
Yeah. I
Yes,
have
sir,
two
please,
questions.
sir.
I have two questions. It's a very nice talk, madam. Partly my question was asked by Professor Kagli. I just want to know whether every galaxy as a black hole is an experimental fact or a theoretical construct. If it's an experimental fact, the search for black holes began long ago. So, wouldn't have that search given indication much earlier? That is my first question. Maybe I will ask the second question after your answer.
Yeah. So, okay, I'll try to give an elaborate answer, sir. So, we have in the mass wise, if we see from the mass wise, we have single stars, then we have binary stars, then we have open clusters, and we have globular clusters. Globular clusters are packed, dense group of stars formed very early in the galaxy. So, galaxy halo will have a lot of globular clusters. So, globular clusters are having a mass of 10,000 solar masses, some in that range. Now, we call there is a very thin line between what we can call as a globular cluster and what we start calling as a dwarf galaxy or ultra compact dwarf galaxies, like that. So the galaxies tend to if they have a mass, if a system has a mass of 10 to the 5 solar masses, and it is able to clear the area around it because of gravitational, and it is a gravitationally bound system, of course. and it is able to clear the area around it, um, uh, then we call it as a galaxy. Now, 10 to the 5 is already an intermediate mass galaxy, 10 to the 5, 10 to the 6, and we have seen black holes, or we have indications of black holes even in that. On the high mass end, 10 to the 12 solar mass galaxies, there is definitely evidence in the massive ellipticals, which I showed you. There is definitely evidence of supermassive black holes in terms of the spectra we take, in terms of the gas motions around the center of the galaxy. The gas will be moving in a rapid manner. So that is already there. So from 10 to the 5 solar masses to 10 to the 12 solar masses, I think we have evidence of black hole at the center. Also, even sometimes the globular clusters are thought to have stellar black holes, which is yet to be confirmed in detail, because the mass is so much. 10 to the 4 solar masses are higher. So we probably there are some stellar black holes already there in globular clusters also. So only thing is in the dwarf galaxies it is at the center and it is accreting material.
Thank you, madam. My second question is, I saw some galaxy with its different orientation. Is it possible for James W telescope to capture different orientations also?
No, sir, the image is rotated.
Oh, I see. Right. Okay. Thank you.
Yes, sir. I think there are no more questions. Uh, we have to thank Dr. Ramya Sethuram for excellent talk, and she has clarified almost all the doubts raised by our viewers. And I think we have from other state also, including Dr. Srikanta from Dubai. Anyway, we thank all our viewers and also KPA members. And from Karnataka Physics Association, again, we thank Dr. Ramya Sethuram, IIA, along with Jnanadhara, because Jnanadhara is supporting this talk every Sundays. We have to thank Sudha, then Sandhya and Dr. M.K. Raghavendra, because they are all cooperating with us, providing this Zoom platform. So we thank other invitees. I think some invitees are also there in this talk. From KPA, Karnataka Physics Association, we thank all of them. And especially Dr. Ramya, who has explained, there are some students from in our YouTube, and for those students especially, she has talked about the components of the telescope, like primary mirror, secondary mirror, then eyepiece. I hope that even the students have also understood this talk.
Sir, we have to thank
Thank you
Professor
again.
Raman. Professor Raman.
Yeah, Professor Raman is providing us YouTube, and we have to thank from KPA. And again, let us thank from KPA all the viewers. And of course, we are closing this issue. Thank you, madam. Thank you again. Thank you all
Thank you.
our colleagues.
Okay, just close the meeting. You can, since you are the host, you can close the meeting.
Sir?
Close the meeting. You are the host, no? You have to
ನಾನು
close.
ಇಲ್ಲ ಸೇತು ಇವರು ವೆಂಕಟರಾಮನ್, he is the host.
Anybody can close.
Yeah,
the
Venkataraman,
host
you can
close the meeting. Yeah. Okay. Let us hope to meet next week at the same time.